Section 1.1, Review of Functions. Being that we are going to use a lot of concepts from, say college algebra or something of that nature, we're going to dedicate some time here to reviewing some of these big concepts. The first of these is the idea of a function. A function f consists of a set of inputs, a set of outputs, and a rule assigning each of those inputs exactly one output. The set of all inputs is called the domain of the function. The set of all inputs is called the range of the function. So we have a function given here, f of x equals 3x squared plus 2x minus 1. Now we want to evaluate this at three function values, the first of which is negative 2. So to find f of negative 2, that will be 3 times negative 2 squared plus 2 times negative 2 minus 1. I'm evaluating, replacing every x with negative 2 in this case. All right. By doing that, I get the value of, let's see, the first one is 12. 12 minus 4 minus 1, so this is a grand total of 7. So f of negative 2 equals 7. Simple enough. Now let's evaluate that at the square root of 2. So 3 square root of 2 squared plus 2 square root of 2 minus 1. So the first will be 2, so that's 12 again, plus 2 square roots of 2 minus 1, and that will simplify, oh, actually that's 6. Scratch that. Square root of 2 squared is 2 times 3, so 6. So this would be, if we combine terms here, 5 plus 2 roots of 2. And that would be the f of square root of 2 equals 5 plus 2 root 2. Our third function value is a plus h. Now this is not a value per se. We don't know what a and h are, but this will come in very useful in our next chapter, being able to evaluate things like this. So this would be 3a plus h squared plus 2a plus h minus 1. Well, a plus h squared is a squared plus 2ah plus h squared. I'm going to go ahead and leave the rest of that be. All right, well, that would be 3a squared plus 6ah plus 3h squared plus 2a plus 2h minus 1. Being that we cannot combine any of those together, that is our answer. Now, in our section on limits, and specifically Chapter 3, finding derivatives, some of these things will cancel out. So that's why I say we will use this, but things will simplify quite a bit. Example 2. For each of the following functions, describe or determine the domain and range. Now we're going to give it or describe it in interval notation and set builder notation. Okay, now this first one is a quadratic function. Okay, so it's going to look something like this, because it's actually in vertex form. It is shifted to the right 4 and up 5. And as I said, it's a parabola opening up. So its domain is all real numbers. You can evaluate it at any value of x. But its range, the outputs, well, if you look at the graph, the outputs are always greater than or equal to 5. It is always at 5 or above. So putting that in interval notation, and we'll throw set builder notation over here. Interval notation, all real numbers would be negative infinity to infinity. We are not including either of the ends there because they are, well, infinity, they're directions. We can go towards infinity, but we don't actually get to infinity. So that would be the interval notation there. Well, in set builder notation, it's a whole lot better. We have x such that x is a real number. All right? They both represent the same thing, They're just written two different ways. Now, often interval notation is used. In fact, it's used a little more frequently. But set builder notation it's very descriptive. It shows you exactly what's there, so they're both valuable. Now, interval notation for greater than or equal to 5 would be a left endpoint of 5 going on to infinity, and we are including 5 because we have a greater than or equal to. Set builder notation would be y such that y is greater than or equal to 5. Okay. Part B of this. The domain for this function would be anything that we can plug in that does not make us have a negative square root. Okay, we want real values here. So we want, in the end, for our domain to be the numbers such that 3x plus 2 is greater than or equal to 0. We can take the square root of 0, just not a negative number, and get a real value. So that would mean if we subtract 2 divided by 3, x is greater than negative 2/3. So in interval notation, we would write that as negative 2/3 going on to infinity, including negative 2/3. And in our set builder notation, so again, I'm writing the same description twice in two different forms. X such that x is greater than or equal to negative 2/3. Now our range will be a little bit trickier because you can plug in anything greater than or equal to negative 2/3, but what outputs do you get? Well, if you evaluate that at negative 2/3, you actually get negative 1. So our outputs are greater than or equal to negative 1. In this case, our graph looks like this. We have our lowest point here. This lowest point is at negative 1 is the y value, and negative 2/3. So the domain is going to the right of negative 2/3, greater than or equal to, and the range is greater than or above negative 1. So this would be y, such that y is greater than or equal to negative 1. Okay. This next function we have is a rational function. The problem we have here is that we cannot divide by 0. Well, what number could you put in there that would make that 0? Well, 2. So x cannot be equal to 2. That's my scratch work. So my domain over here is, well, my interval notation for this would be negative infinity to 2. And if you notice, we are not including 2. We're not including 2 in either of those intervals, so it's actually excluding 2. That's the way to write that. In interval notation, we have x such that x is not equal to 2. All right. Our range, this function actually has a horizontal asymptote of 0. This function is never actually 0. The graph looks something like this. We have at the value of 2, an asymptote, and it does this. So our y value is not 0. So we'll write that as negative infinity to 0, union 0 to infinity. And in set builder notation, y such that y is not equal to 0. Moving on, finding points of interest. Okay, there are a few points that we really want to know about functions. Those are zeros, which are values of x such that f of x is equal to 0. And then there's the y-intercept, which is where instead of f of x being 0, it is where x equals 0, and so therefore we have the point 0 f of 0. So for each of these functions, find the 0, possibly more than one, and the y-intercept if it exists, which there's almost always going to be a y-intercept unless we have a rational function, something like that. There are a few cases like that. So let's go ahead and begin with that. Find the zeros means I'm going to set this function equal to 0. So, whoa, that wrote twice. So the zeros, we're going to set that equal to 0. Which, if we solve that, subtract 2 divided by -4, that is -1/2. So we have an x-intercept as 0 at -1/2, which we're going to sketch this. So at -1/2, let's just call this point 1, or -1. There's our x-intercept. Now, to find our y-intercept, we'll evaluate this at 0. So -4, 0 plus 2 will be a value of 2, so we have the point 0, 2. Just like over here, it's -1/2, 0. So we have the point 0, 2. Now I happen to know that's +1/2, that's the problem. Alright, that just seemed sort of strange. That should be +1/2, which makes this point, okay, let's call that 1. It's 1/2. There we go. That's a little better. Okay, so we have a linear function here, so it is going to be in a line, and therefore that's our sketch. And our second function here, find the zeros. Alright, +1 equals 0. Alright, subtracting 1 from both sides, we get the square root of x plus 3 equals -1. Squaring both sides, x plus 3 is +1, which makes x equal to -2. Now I'm going to go plug that back in to make sure that this works. If I evaluate my function, -2 plus 3 plus 1, this ought to come out to be 0, because that's what we set it equal to. That would be the square root of 1, or 1 plus 1 equals 0, and that is not true. So there's actually not an x-intercept. Okay, and in fact, this is a square root function. I'm going to go ahead and sketch the graph over here. Actually, no, let's find the y-intercept first. This was our x-intercept, and there is none. Alright, so our y-intercept, we will plug in 0, so the square root of 0 plus 3 plus 1, which is 1 plus the square root of 3. So this function has a y-intercept of 1 plus the square root of 3, so that is roughly 2.73. 2.73. 1, 2, 3. There's our y-intercept, and it does not hit the x-axis, which means it's going to curve up this way. So we have a function that looks kind of like that. Alright, let's move on to our next question. Example 4. If a ball is dropped from a height of 100 feet, at time t, okay, then this height is given, okay, I misread that. If a ball is dropped from a height of 100 feet, its height at time t is given by the function s of t equals -16t squared plus 100, where s of t is measured in feet. The variables did not show up here. S of t is measured in feet, and t is measured in seconds. The domain is restricted to the interval 0 to c, where t equals 0 is the time when the ball is dropped, and t equals c is the time when the ball hits the ground. So let's go ahead and make a table and see what is going to happen to this ball over time. Okay, so at a time 0, Since we are told the domain is restricted, we start at 0 and we continue on until we find where it hits the ground. After that point, it really doesn't make any sense. All right, at a point of 0, t equals 0, that is going to be 100. So it begins at a height of 100. All right, let's see. Go to 1/2. So at 0.5, it's at 96 feet. At 1 second, we're at 84 feet. At 1.5 seconds, plugging that in, we are at 64 feet. At 2 seconds, we're at 36 feet. And at 2.5, we're at 0. So the time that it hits the ground is 2.5 seconds. Okay? So the domain of this function is 0 to 2.5. Now we could have very easily found that point where it hits the ground by finding the x-intercept. If we set this equal to 0, we should get, in fact, when we solve that, 2.5. All right. So sketch a graph of this function. Well, we know it starts at a height of 100. So say this is 100. This is 2.5. This is a quadratic function with these x and y intercepts. So we have something like this. Now the reason we ignore what happens over here is because here time is less than 0. That does not make much sense. Same thing in this quadrant, and here our height is less than 0, which means we are in the ground. Doesn't make much sense there either. So we restrict ourselves to the first quadrant. All right, next topic we need to touch on is combining functions. Given the functions f of x equals 2x minus 3 and g of x equals x squared minus 1, find each of these functions and then state its domain. So f plus g of x is the first one we have, and that means exactly what it looks like. We have our f plus our g, or f plus our g, which would be x squared plus 2x minus 4. Now, the domain of any quadratic function in this manner, it's a polynomial really, the domain is all real numbers, so negative infinity to infinity. All right, next we have f minus g. Same idea, different operation. Minus x squared minus 1, which would be negative x squared plus 2x minus 2. And that is f minus g. Now, same idea here. It's a quadratic, so our domain is negative infinity to infinity. You might wonder, if we're always going to get a quadratic, then why are we even worrying with that? Well, there are a couple of places where that will not be the case. So f times g is going to be 2x minus 3 times, where'd my function go? Minus x squared minus 1. So x squared minus 1 there. Okay, multiplying this, we will get a 2x cubed. 2x cubed minus 2x minus 3x squared plus 3, which I'm going to rearrange slightly. 2x cubed minus 3x squared minus 2x plus 3. Our next operation is division. So we'll take our f divided by our g. F divided by our g. Now, what is the domain of this function? Well, the numerator is all real numbers. The denominator, its domain all on its own, is all real numbers. However, we cannot divide by 0. So what values would make this denominator 0? Well, x squared minus 1 equals 0 would give us x equals plus or minus 1. So our domain is x is not equal to negative or positive 1. So I'm going to write our domain in this way. Negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. The same way we skipped them previously, except now we have 3 intervals because we're taking those 2 points out. Oh, and I did not write that here. Our domain on this last one was negative infinity to infinity still, but when you're dividing, be very careful about the domain because we end up dividing by 0 most of the time there. All right, example 6. Consider the functions x squared plus 1 and 1 over x. Find g of f of x and state its domain and range. So g of f of x means that I'm evaluating g of x at f of x. So in this case, that would be g of x squared plus 1. Now g is the reciprocal function, so this is 1 over x squared plus 1. So there's our function. There's g of f of x. The denominator here is never 0. It's always positive. So our domain is all real numbers. Okay, now our range, this is a reciprocal function or a rational function. So we have a horizontal asymptote here of 0. So we actually get the y values are everything except 0. This is a function, like I mentioned earlier, that does not have a y-intercept. It doesn't actually... Oh, scratch that. It has a y-intercept. It doesn't have an x-intercept. All right. Evaluate g of f of 4 and g of f of negative 1/2. I'm going to go ahead and use my function g of f of x. Go ahead and just write that in here. Equals 1 over x squared plus 1. So evaluating that at 4, I'm just going to write that differently there. Evaluating that at 4, we get 1 over 17. All right, g of f of negative 1/2, because we already know what the function is, now we found g of f of x, we can evaluate that at negative 1/2. So that would be 1 over negative 1/2 squared plus 1, positive 1/4. So that would be 5/4, and that should be 4/5. Find f of g of x. We're going in the opposite direction. So this is f of g of x. G of x is 1 over x. And since f is x squared plus 1, this is 1 over x squared plus 1. We squared 1 over x. The domain of this function is all real numbers except for 0. We can't plug in 0 there. We would divide by 0. Now the range, this is going to have a horizontal asymptote at 1 actually. The first part's going to be has a vertical or horizontal asymptote at 0, so we cannot get a range value of 1. All right, now we're going to evaluate that function at 4 and negative 1/2. If we evaluate that at 4, okay, f of g of 4, that would be 1 over 4 squared plus 1, 1/16, so that is 17/16. And if we evaluate that at negative 1/2, okay, we will have 1 over negative 1/2 squared plus 1. That is 5. Squaring that, we get 1/4. Flipping that over, taking the reciprocal, we get 4 plus 1. Okay. Consider these functions. Evaluate f or g of f of 3 and g of f of 0. So this means g of f of 3. Well, f of 3 from here, this table, tells me that's -1. Or -2. And then g of -2 is 0. So my end result there is 0. Now if I want g of f of 0, f of 0 is 4. So that's g of 4, which then is 5. Now we want to state the domain of g of f of x. Well, notice that f of x takes a particular set of numbers. We have -3, -2, -1, 0, 1, 2, 3, and 4. Takes those numbers to the values -2, 0, 2, and 4. And then g of x takes -4, -2, 0, 2, 4, takes those to the values 1, 0, 3, and 5. Alright, so the outputs of f are these three. Well, if we only consider those 4 numbers there, 4 outputs, as the 4 inputs here, what we actually get is that the domain is that set -3, -2, -1, 0, 1, 2, 3, and 4. But our range ends up being everything except for 1. It doesn't actually get mapped to. Because we're not including this -4, and the -4 actually goes to 1. So only these 3 are part of our range. Next, let's find f of 3. Well, f of 3 is going to -2, and then f of -2, we're just using that same chart again, that goes to 4. Okay. F of 1. F of 1 is -2. So it's f of -2, and then that goes to 4. Again. Okay. State the domain and range of f of x. Okay, again, f maps these numbers here to these. Well, where do these 4 go under this table? -2 goes to 4. Okay, so our output is a 4 there. Okay, so our domain is simple. Our domain is -3, -2, -1, 0, 1, 2, 3, and 4. Our domain, where do those go? Well, again, -2 goes to 4. 0 goes to 4, so no need to put that down again. 2 goes to 0. And 4 goes to 4, which we already have written down there. So our range is actually just as the set 0 and 4. Okay. Stores advertising a sale of 20% off all merchandise. Caroline has a coupon that entitles her to an additional 15% off any item, including sale merchandise. If Caroline devices to purchase an item with an original price of X dollars, how much will she end up paying if she applies her coupon to the sale price? Okay. We have a function here. The sale itself, I'm going to call it S of X, is 20% off. So 0.8x, that is the sale price. Now her coupon gives her 15% off, so it's 0.85x. It takes off the cost is now 85% of what it was. So if she applies both, we're actually finding coupon of sale price of x. So that is 0.85 times 0.8x. And if we multiply those two, that is 0.68x. So how much will she end up paying? 68%. She'll end up paying 68% of the price. So she doesn't actually get what you might think she'd get off, but it's multiplying those two. All right. Our last concept for this, even and odd functions. For something to be an even function, it means that f of x and f of negative x have the same value, which means it's symmetric about the y-axis. Okay, means the value over here and the value over here are the same. So it's symmetric about the y-axis. If f of negative x equals negative f of x, then it's an odd function. That would mean something like this. This value over here is the same as this value over here. So the simple way to work this is evaluate your function at f of negative x and see what you get. If it's the same thing, then it's even. If it's the opposite of what you had originally, then it's an odd function. So let's go into an example or two. Determine whether each of these are even, odd, or neither. Well, let's evaluate this at negative x. That would be negative 5, negative x to the 4th, plus 7, negative x squared, minus 2. Now, if you notice, squaring these makes them positive. And we get exactly what we started out with. Therefore, f of x is even. Can say that because f of x equals f of negative x. All right, next, let's evaluate this function at negative x. 2 negative x to the 5th minus 4 negative x plus 5 is negative 2x to the 5th. The odd exponents actually bring a negative sign out. Okay, now this function is not equal to the original function. It's also not equal to the opposite because of this 5 here. It's still a positive 5. So this is neither. Okay, because that positive 5, it is not even and it's not odd. All right, part C. Evaluate f of negative x. That is 3 negative x over negative x squared plus 1. So negative 3x over positive x squared plus 1. This is not equal to the original function. However, it is equal to the opposite. We have one negative sign in this entire expression. So f of x, or I should say negative f of x, equals f of negative x. Therefore, f of x is odd. Last question, find the domain and range of the function. Now, this is an absolute value function. This is an absolute value function. And it is, in fact, shifted to the right 3 and up 4. So the graph of this is to the right 3, up 4. Its vertex is right here. And it is opening up because we have a positive a value. We have a positive a value there. So the domain is all real numbers. Real numbers. And the range is y is greater than or equal to 4. The lowest point is at 4 and it goes upward from there. So 4 to infinity. and that is our range. All right, that brings us to this section. There's a lot of information in here, but you should be familiar with all of these things as we go forward. Okay, and there's actually some more in the next section we want to make sure we are good with. All right, there we go.